All right, this afternoon session, we're going to continue the same theme we had. And Will Galton is here from Power Corp. He's going to talk a little bit about a project they're doing, which was introduced this morning. Will's an electrical engineer with them who I think would rather be snowboarding today, but he's here to talk to you. Okay.
Thanks, Edo. I guess it's an interesting chain of events that see me here today. About a week ago, I was sitting at my desk in Australia and the boss came in and said, "You're going to Alaska." I said, "Oh, okay. What to do?" And he goes, "I go to a conference." I said, "Oh, good, as long as I don't have to talk." Because that's probably the worst thing that I see in my life. But the thing that makes it worse is I was a snowboard instructor in a past life, so I'd rather be out there. But anyway, so I guess we're going to talk about the funny cousin to wind, who's a little bit scared of the dark and only hangs around for half the day. So what I'll do is I'll talk about a couple of projects that we designed and commissioned over the last few years in I guess the central part of Western Australia. And just to go through, we'll talk about where they are, why, some of the goals and objectives that we had, and why solar diesel, and the concept, the challenges faced, and I guess have a look at some of the results since going live. Now, I guess being a late organiser and getting it ready, some of these slides you would have seen this morning from Russell, but that's, I guess, just a quick overview. And as you can see, we've, I guess, the natural progression from wind and hydro that Russell was talking about earlier was going into solar. So I'll just skip through these since Russell touched on them earlier today. So we'll start with where. So where you see the A mark, that's Marble Bar, and Nullagine about 100 kilometres further south. We have the same sort of issues as you see in this part of the world. It's quite remote. You'll notice there's not many towns between Darwin in the middle of the north and I guess Perth down in the bottom western corner, because it's not. So we have the same sort of issues with getting fuel to site, and transport of equipment to those sort of areas can be challenging. And I'll talk a bit about temperature when we go on, but we had days in excess of 50 C, so I guess that's probably about 130 F along those lines. So handling tools and equipment can be challenging in that respect, as I'm sure you'll see here in the winters. So what were the key objectives and goals of the project? Well, there's the obvious ones, to meet the consumer's requirements for quality power. As Russell touched on earlier today, we have regulators that make sure that the remote communities get the same quality of power as what you get in the city. There's also making it affordable. One thing that Russell didn't mention earlier today is that the cost to the end consumer what you're being charged has increased significantly over the last couple of years in Australia. It started state by state and everyone started getting on board, and in some areas, I think in WA, they've seen about 150% increase in what you're paying for your electricity. Now that's because it was heavily subsidised earlier, and people are coming to the realisation that, you know, if we're going to pay a fair price, then everyone has to do it. Obviously there's the environmental aspect to it, and the old power stations at Marble Bar and Nullagine, when they were built, the town was originally built around them going back 20 odd years ago. With the new noise restrictions that have been brought in Australia, they're not compliant with those noise restrictions, so they either have to put in some sort of sound attenuation or look at building new greenfields power stations. And also at Marble Bar, they got a flood 2 years ago and the water level went about 2 foot up their main distribution board. Now, one of the key goals that our end customer had, Horizon Power, the utility in the area, was to develop a modular, automated, renewable and scalable, I guess, platform to work with going forward. Now, what that means is, on the modular side, being able to increase either the renewable part, the solar, and or diesel. With the automated, well, I think that's fairly straightforward. The renewable again, and scalable, by being able to increase the size without the need for a lot of extra, I guess, ancillary equipment, just putting the plant in there and it should work. And then the last one again is pretty self-explanatory. So why solar diesel? We looked at going down the wind path at these sites, but the wind regime was marginal, and it just didn't make sense with the numbers we're seeing in some of the modelling. Now you notice here that the cost of diesel in these sites works out to be about $8 a gallon, and that's what they pay at the Bowsers there. Now the utility will get it cheaper, but we're not privy to that information. That's something they weren't willing to share. But you can assume that let's say 3/4 of that price. Now obviously the load's increasing, people have got more disposable income, and with the cheap air conditioning split systems that are available on the market, everyone's just putting them into the houses out there to make things a bit easier. As you may remember, it was 130 F out there. Now there's good solar resource year round, and the flat plate single axis tracking in the modelling turned out to be quite attractive, hence we went down that path, and also just to develop the model for the rest of the sort of area that we were talking about. Now I guess looking at the concept, some key numbers to think about going forward is that the min and maximum loads at Marble Bar were around 600 and 200 kW, and a little bit less at Nollongine. The utility required an N+1 setup, so I guess to answer Ian's question that he had to Russell earlier today about the diesel off functionality, we were restricted by our end client in this application, and I'll talk a bit about some things that happened during commissioning that verified that it is possible to go down that route. But that's something that we will, I guess, work with going forward with the utility and hopefully get them across the line, because it's a feather in their cap but also in ours. Now, one thing that I've picked up since being here and talking to people is the long lead time from when I guess you first have the idea to when you get something where you can cut the tape and everyone's happy. On projects such as these two, it took 12 months to come up with a design that the customer was happy with, and we went through 10 revisions of all sorts of different changes, and we ended up coming back to pretty much what was set out in the first place. But that's the process that you have to go through, and as consultants and I guess a company that builds them, we need to educate people, and I guess that's why we're in these sort of forums, to learn from each other, but also the education part. Obviously we did the HOMA modelling, and we do a lot of high-speed dynamic modelling using a computer package, software package called Power Factory, and it's put together by a company called Digslent from memory, and that gives us the ability to do the short 1-second modelling and really get a good understanding of what's going to happen in certain scenarios. Now, the good thing about us having a full hands-on approach is we get to see the data once the site is commissioned, and we can verify our models. So it gives us good real-time feedback, so going forward we can apply that knowledge. And obviously the economic and virtual models. So at Marble Bar, the plan was that we'd put in 4 Series 60 Detroits rated at 320 kilowatts, a 300 kilowatt PV flat plate farm, and a 500 kilowatt flywheel. As you'll see, there's no battery storage in this application. There is merit to it, but for this particular application, it wasn't used. Nullagine, fairly similar, 1 less diesel, a little less PV. So through the initial phases when we thought about the concept, we're able to get people to put together a plan and I guess a visual model of what the power station might look like. Now, to some people that have seen some of our other sites, sort of look similar in some respects. The control room is the elevated one right in the centre of the screen now, and it goes through and it's got the power store and the generators that we'll see in a minute just off to the right, and the whole plan of I guess having the modular setup is that you can remove plant when the community numbers decrease. We have that in Australia. The Indigenous people will move from community to community. So when the load increases or decreases, it gives the opportunity to pick plant up and move it across where it's needed. All right, so some of the challenges that we faced, obviously there's the remote location and temperature, but I guess finding a solution that fitted what our end customers' requirements were, trying to meet the Mars concept. Working with a renewable source that we hadn't really worked with on a large scale, that being the solar. And some of the things that were very challenging was the response to set points that we were given, that we were giving to the solar farm. Through our other projects, wind turbines generally respond pretty quickly. And when we first turned up and met the solar people, they said, well, we can respond in about a minute. And we said, well, we're used to 1 second. Can you kind of come and meet us a bit closer at our end? So after some long drawn out negotiations and a lot of development work on their side, they managed to bring it into about 4 seconds. And that was long enough for us to, I guess, put all the control around it to make it all work. And the other thing that was interesting was the solar farm's response to solar radiation. I've got some slides that'll bring up those in a minute, so I'll talk to that very shortly, or right now in fact. So you might expect, just to give you what the scale is, on the right-hand side, that's radiation in, I think, watts per square metre, and the top, along the very top, is about 1,000. It is 1,000, and the blue is just the temperature, so that's, I guess, a little irrelevant for this slide. But you'll see that, and that's 3 days that you're looking at there, and it kind of looks as though the sun comes up and behaves itself, and it's shining away. And on days like this outside, it is. But we knew that wasn't the case, and this is what the solar does look like. So, you know, you get your days where you have a lot of cloud events, like the first day there, and we saw output go from 100% to 20 and back to 100 in a couple of seconds. Now, you know, look, everyone's talked about the different technologies they're implementing to address that. We use the flywheel because of the quick response times. And I guess the other thing is you need to provide spinning reserve. And when you've got loads at around sort of 600 kilowatts during the middle of summer, if you have 300 drop off, you need to be able to catch that. And the step load capabilities of the diesel generators weren't able to catch that full step. And with the power store rated at 500 kilowatts, it gave us that functionality. One other thing to notice is on day 3, there wasn't a lot of solar at all. So I know people are pushing for the whole renewable thing, but in applications such as these where there's no wind resource and the solar is intermittent, you do need that diesel background. So why were we using the flywheel? I touched on it briefly, but the step load capability to catch the solar if it tripped offline, but also if one of the diesels went offline, it gave us that comfort that we could carry the spinning reserve in the flywheel and not have to run extra diesel generation. The power versus energy, well look, the power store can deliver full energy regardless of its state of charge. So if it's at say 40% state of charge, it can absorb or sink or source 500 kilowatts for the rest of that state of charge. We have set points obviously whereby we'll get down to a minimum state of charge, and then we'll have to bring on other diesel generation so the flywheel doesn't run out of power. Frequency and voltage, Russell touched on that earlier, with the flywheel providing both real and reactive power. Now, I know one of the questions that was asked of Norm is what the parasitic load is. In our application, because we put all the power electronics and the flywheel in a 40-foot container and it's 50 degrees outside, we require a fair bit of cooling load to keep all the power electronics within an acceptable range. So at this particular site, we're seeing about 15 kilowatts. Now, people will say that's quite high, and I guess it is, but the benefits that the flywheel provides far outweighs that 15 kilowatts. I guess a simple analogy would be having to put another diesel online, and they can run down to about 10% of their nominal rated load, so you're talking about an extra 32 kilowatts worth of diesel just on site. So that's a very simplistic way of looking at it, but it gives you a bit of an idea. And also, the spinning reserve allows us to run one diesel at night time. So when the solar's not there, rather than having to run two diesels in case one trips offline, we're able to run one, and we have had an instance where a diesel went black at night, and the flywheel held the station up for 30 seconds to bring another diesel online, and the power supply into town was uninterrupted. So, unfortunately, Peter, I think I've offended you already, as you can see up the top there, but I'll talk to that a little bit. So during the winter months, when the town loads down around sort of 300, we're able to essentially feed most of the town with the solar. I'll try not to use the P word. Now, the diesel off functionality that I touched on briefly, we have a group of German engineers that come over and work with us each year, and those people that know Jürgen will understand that he likes to train some of his German colleagues up. And when we're doing the testing of the generators, we asked one of the German boys to bring another diesel online. He understood that he wanted all of them offline. So he turned them all off, and we came in and did our step load tests, and all the lights stayed on, and we said, oh, well, can we have a look at the graph of the diesels? And they weren't on, so it was just the flywheel and the solar going. So we ran some further tests, and we're happy that the station will be able to run in that diesel off mode. However, as Russell alluded to earlier, there's the fault current issue that needs to be addressed and worked through with the end customer. So we're seeing greater than 65% of the daytime energy coming from the solar. I've touched on the running one diesel at night, and the estimated fuel savings based on what we've seen to date after going live in May last year is about 412 litres, or about 100,000 gallons. And if you're paying, I guess, anywhere from $6 to $8 a gallon, it starts to add up pretty quickly. It has given us a template going forward, and one little anecdotal thing I'll put in there is we've had one blackout to date, and the station operator won't be overly happy with me telling the story, but it's unmanned on weekends, and on a Friday he was down in the fuel farm when the fuel delivery came in, and he was leaning against the fuel tank, but he didn't realise he was leaning on the emergency stop button in the fuel farm. Now, that emergency stop is just for the bulk tanks. So he left, and the station was still live. So he went home on the Friday, and Sunday night everything went black. So he went up to the power station to start it, and he couldn't get any of the diesels to start. Now what had happened was the day tank ran out of fuel, and then the belly tanks and the generators ran out of fuel, and all four of them did it. And when he turned up to site, he could see each generator's been on, and there's alarms on it. And sure enough, the last 30 seconds of power was held up by the power store, and then it all went black. So that's pretty much what I wanted to do. There is a video here that'll play in the background of the site itself, so you get to see, I guess, the location that we're working in. And it's a bit of marketing guff, but I think this is probably a good opportunity to take any questions while it's running.
Was dust on the solar panels an issue, and did you do anything to cool the solar panels with the high heat to mitigate degradation?
Okay, to address the second part, no cooling on the solar. To address the first part, there is monitoring happening by the utility. They're going to crunch some numbers, and they've started cleaning certain sections to see what the efficiency is like in those particular areas. And after a year, they're going to see whether or not it's worthwhile paying someone to go out and clean them. So hopefully this time next year we can answer that question with a bit more authority.
Did you say the diesels can run down to 10% of rated load?
Correct.
Were there special modifications required, or are they?
There is, yeah. These particular gensets were built by the utility themselves, and they're based on the low diesel technology that Power Corp and Diesel and Wind Systems in Western Australia developed, I guess, over the last decade.
As a percentage of total fuel spend, what, that 110,000 gallons savings, what percentage was that of?
Good question again. The utility hasn't provided that information to us, so as a percentage, I can't comment. That is something we're trying to get out of them, so I can, I guess, speak to those sort of things, but they're the numbers that they're telling us so far.
What kind of inverters were you, solar inverters were you using?
The inverters were supplied by the solar team, and I believe they're the Sunny Boys, the SMAs. Is that right, Russell? Yes, they are. Up the back.
Are they tracking solar panels?
Single axis. We may see in one of the pictures that come up behind me, there's 3 rows of solar, and they've got, each row's got a motor sort of stationed in the middle, and they'll track from, as soon as the sun comes up, they'll pitch over to watch the sun, and they adjust so they don't cast shadows on each other, and then they'll follow it right through till the sun goes down, or until the shadows start to take effect, and then they just lay dormant for 12 hours until the sun comes back up the next morning.
Why do you have the control enclosure raised so much?
I think it's probably a bit of historical reasons there. It's something that the customer wanted. At some of the other wind diesel power stations that we've built, we've always had the feeders coming in underneath the building and straight up into the main distribution board. It cuts down a little bit on some of the concrete requirements and excavation underneath the building, and allows fairly easy access in there if you want to add on further feeders later on. All good?
Right, let's give Will a hand.